Thank you. So good evening, everybody. Thank you for inviting me. Today, I'm going to be talking about a semiclassical WKB problem for the Dirac operator with a decaying potential. That's a work done along with my advisor, Spiros Kambisis, from the University of Crete. Before I start, let me say that I would like to express my sincere gratitude to all of you, the organizers and the financial supporters of this conference, especially the Demet of Yaroslav State University, along with the Center of Integrable Systems and Nonlinear Dynamics, the Liverpool Whole University, and the company Tensor. And of course, I would like to thank all the individuals that gave me the opportunity to visit the Moscow State University through the Erasmus Plus research scheme, and especially Professor Alexander Ivanovich Aptekarev. Today we shall be focused in the semiclassical behavior of the scattering data of a non-self-adjoint operator with a fairly smooth potential that decays at infinity. What we shall do is we will utilize some of Olver's theory to provide rigorous semiclassical analysis of the scattering coefficient along with their Bohr-Sommerfeld conditions and their corresponding norming constants. Due to the restricted time, I would like to mainly be focused on the eigenvalues that lie away from zero and to the behavior of the reflection coefficient away from zero as well. But the strategy that we shall present in this talk parallels the ones for the remaining cases. So if anyone wishes to see that, you can just find the full details of our publication on arXiv. So our motivation, our starting point was the 1+1 focusing nonlinear Schrödinger equation, and especially the following initial value problem, where, as you can see, the parameter h bar is a positive number, and the initial data, namely the function a, is assumed to be positive, even bell-shaped of some smoothness, and of course that tends to zero for large x. Let me show you how a solution of this problem looks like. In this figure, you can see a numerically calculated solution of this initial value problem, where the parameter h bar is 0.1, and the initial data is a hyperbolic secant. As you can see, on the horizontal axis, you find x, while on the vertical axis here on the left, you find the evolution of time. The graded scale here on the right ranges from deep black to bright white, depending on the order of magnitude of the squared of the modulus of our solution. So as you can see, lots of interesting situations appear. But let me ask a question concerning this initial value problem. Let us suppose that this parameter h bar, which you can think of as Planck's constant, let us assume that it is small compared to x and t. What is the behavior of the solutions of this initial value problem when we let this parameter tend to zero? Problems and questions like this arise in lots of interesting areas of the sciences. For example, you may encounter them in propagation of light in nonlinear optical fibers, or it may be thought of a question in hydrodynamics, where small amplitude gravity waves are produced on the surface of deep and viscid water. And of course, there are some so-called Thomas Fermi limits concerning Bose-Einstein condensates. But now let me introduce you the concept of how can one solve such an initial value problem. What you do is you apply the well-known IST, the inverse scattering transform. So the scheme for solving such a Cauchy problem was produced back in the 1972 by Zakharov and Shabat. So you start with your initial data and you attach to it what is being called a lax operator, a lax pair, which consists of a lax operator, which in our case is a non-self-adjoint, the non-self-adjoint Dirac operator. So by doing this, you calculate some scattering data that relate to the initial data. And these scattering data are comprised of the eigenvalues of our lax operator along with their norming constants and of course the reflection coefficient. Then what you do is you let these data evolve with respect to time, and then you take these evolved scattering data, and by doing an inverse scattering transformation, which is like solving a sort of Gelfand-Levitin-Marchenko equation or a Riemann-Hilbert factorization problem, you arrive at your desired solution. So as you can see, in order for this approach to be achieved, we have to have a very good and rigorous semiclassical knowledge of the semiclassical behavior of our scattering data. So this is why we would like to investigate this as zero, the scattering data at time zero. The direct scattering problem is written as the one shown in the box. Here, the DH stands for the non-self-adjoint Dirac operator, which is defined here in the middle of the screen, while U, the boldface U, is a function from R to C squared. Lambda plays the role of the spectral parameter and of course is a complex number. I would like to emphasize that in the definition of our operator, the function A is the same as the initial data of our focusing nonlinear Schrödinger equation. Now, let us start by investigating the behavior of the eigenvalues of our scattering data. So what we shall do is we will start by setting the ground for our problem. Then we shall do two consecutive transformations to take our problem to one that can apply the Olver's theory. And then by finding approximants of solutions of our transformed equations and asymptotics, we shall connect these in order to get the well-known quantization condition of Bohr and Sommerfeld. So our scattering problem is this, like this, and we treat our operator as a densely defined on L2. What we would like to investigate is the behavior of the eigenvalues when the H bar parameter goes to zero. Okay, so what do we mean when we talk about the eigenvalues? For every fixed H bar positive, we say that the lambda is an eigenvalue of our operator if the scattering problem has a non-trivial solution in L2. Since our operator is a non-self-adjoint, we expect it to have complex eigenvalues. So we know that the eigenvalues of DH for every H bar are simple, symmetric with respect to the real axis, and do lie on this interval of the imaginary axis. So following on, we shall utilize this symmetry of the spectrum, as you can see. Okay, so we have this scattering problem, and now what we shall do is transform it to a single equation. Okay, so we have the following proposition. Finding the discrete spectrum of our operator is equivalent to finding the values of mu, that is a positive number less than the value of A at 0, which, remember, since it's a Bell function and an even one, it's the maximum value of our potential. So in order to find the spectrum of our operator, we need to find those mu's for which this equation has an L2 solution. How can one prove such a thing? Well, first we write I times mu for lambda and consider mu to be a positive number less than A0 due to the symmetry of our potential. So we only take into account the eigenvalues that lie on the upper half plane and do the following change of variables. We, the one you can see down here. So what we get actually is two solutions, two equations, two equations, but we choose only the one in order for this function to be well behaved. I mean, so that it doesn't have any singularities. So this is the equation that we shall take in order to move forward. But before we arrive at our last stage, we shall need another one change so that we can apply Olver's theory. So what we do is let us fix a constant A naught, which is a positive and less than the maximum of our potential, and take a mu that lies in this interval. So here down in the figure, mu is on the vertical axis, so it's it lies here. Observe that when mu is in this interval, the equation A of x equals mu has exactly two solutions, which are the well-known turning points or transition points, which of course satisfy this symmetric relation. Observe that when mu reaches the maximum value of our potential, our two transition points coalesce into one double at x equals 0. So what we do now is we define a new parameter, let us call it A, that is the right turning point, the positive turning point of these two produced by this equation. Okay, now we're ready to have the equation upon which we will apply Olver's theory. With this new parameter A, our equation is replaced by this one, where these two functions f and g satisfy the following formula. Okay. Now we shall take this equation and do another transformation, a transformation called Liouville. So we introduce two new variables, namely y capital and zeta, satisfying this relation, and we prescribe this quantity to be zeta squared minus alpha squared, where the new parameter alpha is a non-negative one and chosen in such a way that x equals negative a corresponds to zeta equals negative alpha, while x equals a corresponds to zeta equals alpha. So the one who is who knows what this says actually can be able to recognize the existence of a parabolic cylinder function, but more on this topic later on. By integrating this last relation, we arrived at this one, and some further analysis shows that there is a one-to-one correspondence between x and zeta. So this is the equation that we arrived at. For every h bar positive, the equation we started from is transformed to a new one on the Liouville space, where this function psi is to be interpreted as an error term. So what we would like to do now is somehow get rid of it and try to find approximate solutions of this equation. And of course, these solutions will be in terms of parabolic cylinder functions. Okay, but let me translate what this says in terms of our discrete spectrum of our operator. So finding the discrete spectrum of our Dirac operator is equivalent to finding the values of alpha for which this equation has a solution that is both decaying at negative and plus infinity. Now, the main theorem concerning the approximate solutions of our equation is the following. So for each h bar, the Liouville equation has in this region, pay attention to the red part of this plane, has two solutions, y1 and y2, that satisfy these two relations having to do with the functions u and v, which in Ablovich's and Stegan's notation correspond to these ones in terms of Whittaker's function. These are the well-known parabolic cylinder functions. So these two solutions are continuous and have continuous first and second partial zeta derivatives. Also, we do find precise estimates for the error terms, for the remainders. How can one prove such a theorem? So the proof follows four steps. What we do is first we construct a Volterra integral equation for the error term of our equation for this one. Then we write down the Liouville-Neumann expansion for the solution of this integral equation. And as a third step, we confirm that this solution is twice differentiable by constructing similar series for their derivatives. As a final step, we produce the bounds for the error term and its derivative by measuring the Liouville-Neumann expansion. But in order for one to be able to do this, he has or she has to have a continuous error term psi, so the junk term has to be continuous in this interval, in this region of the Liouville plane, and also that this integral converges uniformly with respect to alpha. The assumptions we place on our potential guarantee these two key issues. But remember, there is a disadvantage in this theorem. We do have solutions that are quite good, but unfortunately, they are only true for this part of the Liouville plane, but our equation, our Liouville equation, was on the whole real axis. So what can one do with this? In order to move on, we have to find connection formulae. So what we do is we replace zeta by negative zeta and appeal to the previous theorem to ensure two more solutions, y3 and y4. By finding asymptotics for the error terms, we can find both asymptotics for the two pairs, for y1, y2, and y3, y4. I don't want you to show you too many intricate formulas, but these are the asymptotics for our two pairs. Now, the connection is evident. We write the functions, the solutions of the one term with respect to the solutions of the other pair. So in order to do this, we need to find the so-called connection coefficients. And actually, it turns out that if we apply these asymptotics to this kind of relations, we end up having this proposition, giving us complete knowledge of the asymptotics when h bar tends to 0 of our connection coefficients. These connection coefficients are very important for the theorem that follows, a theorem that tells us the position of the eigenvalues. So suppose that lambda is an eigenvalue lying in this part of the imaginary axis of our operator. So then there exists a non-negative integer for which the Bohr-Sommerfeld condition is satisfied. Conversely, for every non-negative integer such that this half integer multiple of pi times h bar belongs to this interval, there exists a unique eigenvalue of our Zakharov-Shabbat operator that satisfies this inequality with a constant c depending neither on n nor on h bar. Before I give you the last results of this section, let me say something about how can one prove such a theorem. For the first part of the theorem, we use the connection formulas that we derived earlier, and recall that the eigenvalues appear for those values of alpha for which there exists a solution that is decaying both are at plus and minus infinity. This implies that y1 has to be proportional to y3, so this connection coefficient, this sigma 1, 2, has to be 0. And by getting it 0, we arrived at this formula, the Bohr-Sommerfeld condition. For the converse now, existence is shown by proving that there exists an alpha that annihilates this connection coefficient, and uniqueness is proven by a mere application of Rawls' theorem. Okay, let me fix some vocabulary before I move forward to the final results of this section. So let me give you the definition of the WKB eigenvalues. Because consider an eigenvalue lambda of our operator that satisfies this equality, and let alpha sub n WKB be such that this integral equals this half integer multiple of pi times h bar. Then this lambda sub n WKB will be called a WKB eigenvalue corresponding to our eigenvalue lambda. So by using this definition, we have the following corollary of our main theorem. Consider a function alpha satisfying all the assumptions stated before for every non-negative integer n, such that this number belongs to this interval. There exists a unique eigenvalue that satisfies the following asymptotics uniformly in this interval of the imaginary axis. Okay, Since we know the location of eigenvalues, let us find asymptotics for the norming constants as well. So once again, it can be shown easily that for every eigenvalue I times mu, the corresponding norming constant has asymptotics of this kind as h bar goes to 0. But this is a natural thing. We expected something like this to happen because our potential is an even one, and this -1 to the n has to be the case. Also, I should emphasize that this n is the same n on which the mu, the eigenvalue, in other words, depends on. Okay, so now that we have knowledge of the eigenvalues and their accompanying norming constants, we shall find some knowledge. We would like to find some knowledge about the reflection coefficient. So once again, we follow the same strategy. We start with our problem, we write it down in an equivalent way, we find approximants and their asymptotics, and then we arrive at our final result. So once again, this is our initial point where we start, but this time, lambda, the spectral parameter, runs on the continuous spectrum of our operator, which is the whole real line. Since we want to deal with the behavior of the reflection away from 0, we consider an arbitrary delta so that the absolute value of lambda is greater than delta. So we yes.
5 minutes.
Yes, thank you so much. I do have a clock beside me, so yeah. By applying the change of variables, this one, to this problem, we once again reduce our system to a single equation, namely this one. And the proof is essentially the same as I showed you before. Now, from scattering theory, we know that the reflection coefficient for the waves incident on the potential from the right can be expressed in terms of Wronskians of the Yost solutions, namely these solutions that satisfy these precise asymptotics at the infinities. One has this kind of asymptotics, this kind of solutions for this equation. And in order to move forward and arrive at our final result, we would like to find asymptotics of these approximate solutions. Okay, this is easy as far as we know the asymptotics, or we do have precise estimates for these remainders. In this case, this is true. So our WKB solutions satisfy this kind of asymptotics. Okay, now my final result, let A satisfy our assumptions and consider an arbitrary positive number delta. For our reflection coefficient, know that it satisfies these asymptotics as h bar tends to 0, and this is a uniform relation with respect to lambda being away from 0. How can one prove this? You just construct the Yost solutions as WKB solutions, use this formula, which is the definition of the reflection coefficient, and what one has to do is just find asymptotics for these two Wronskians. And this is how you arrive at this asymptotics. As an epilogue, I would like to say that we have already encountered a similar semiclassical problem for a multi-humped potential, a potential that has wells and barriers at the same time. And also, we have investigated a relevant semiclassical problem for the ZS operator with a fast oscillating potential where alpha now is a function that plays the role of the modulus, is positive, analytic, and decaying at infinity, while the phase S is real valued, analytic, having constant limits at infinity. For this last problem, we used a totally different theory to arrive at our results, the so-called exact WKB, in order because the exact WKB needs the analyticity of our potential. So thank you everybody for attending my talk. I hope you found it interesting. I'm open to any questions or critiques that you may want to give me.
Thank you very much. Some questions?
Sorry, was it correct that you demonstrated some numerics? You had some triangular structure, then it disappeared, and you see another one.
Would you like me to share the numerics one more time?
Yes, if you don't mind.
Sorry, I didn't hear you.
Sorry, yes, if you don't mind.
Yes, sure. There you go. Okay. Here it is.
Yes. So it seems that the first triangle structure disappears in some moment, and you have a second one, or not?
Yes, exactly. As time moves on, more complex structures appear. So, in order to speak, this down here is related to a Riemann surface of genus 0. Then you move on to another one of genus 2, and then to genus 4, and so on.
But the first remains, the first triangle structure, it disappears, and the second one appears. Sorry. So
Sorry.
Oh, sorry. Where is the microphone? Sorry, is it here? This one. Sorry, is it correct that you have the first structure disappears or not? The first triangle structure, it still survives.
What do you mean when you say the fast-traveling triangles structure?
No, you have triangle. Then the second structure generated from the first one.
Yes, this one.
But it's some development of the previous. Or it's a new solution, how it looks like.
No, it's the development. It is how it develops when time moves on.
Thank you.
One more question.
So may I make a comment here?
Is your asymptotic formal, or it's you prove the existence, not only estimate the remainder, but prove the existence of solutions with these asymptotics? Did you understand my question?
I didn't hear it. Can you ask it one more time, a little more loud this time?
What about now? Is it better? No. Oh, okay. I cancel my question.
Okay.
Okay. May I make a comment? Yeah. So
Yeah, sure.
it's Dobrachotov.
Please.
So, Nikos, thank you very much for your interesting talk. I would like also maybe to attract your attention to the papers of Kuznetsov, Todorovsky, and Reinhardt about the Klein tunneling. So they considered that the two-dimensional Dirac equation for the graphene. And then they also reduced this Dirac equation to the Schrödinger equation or Sturm-Liouville with the complex potential. And then they construct many interesting solutions. Maybe you can use them in your application also. And another,
I would be in debt to you if you could please send them to me to an email.
Yeah,
I would be in debt to you.
I can. So maybe you ask my email of your. So my email you can find in internet. It's very simple. So
Okay,
S.Dobrokhotov.
Let me ask you your name then, because I didn't hear it.
Dobrokhotov.
Dobrokhotov. Thank you.
Khotov. And then the other fact that actually the problem about the WKB method in the case of the Sturm-Liouville or Schrödinger equation with this potential, the complex potential, was a detail is investigated in the papers of Shkalikov, recent, more or less recent papers, and Andrei Shafarevich. And Andrei Shafarevich, he discussed the question about the Boltzmann-Feld quantization rule in this situation. Maybe it's also will be interesting for you.
I will write you right away, and if you could send me these works, I would be very happy. Thank you.
Okay, so thank you.
Thank you very much.